Algebra I Honors, Lessons 1.7 Logical Reasoning, 1.8 Graphs and Functions, and 1.9 Statistics, Analyzing Data by Using Tables and Graphs. This looks like a lot, and it is. So don't forget, you can always pause the recording if you need more time. So logical reasoning is our introduction into a branch of mathematics called logic, which is a way to look at information and break it down so that it is consistent and we can draw conclusions from it. We got to build you up, and actually a lot of this ties into geometry. I have a little problem with the way this unit runs, and that it kind of throws some random things in it, but they're all good things to know, so I can't be that ticked off. An if-then statement, it's called conditional statement. If-then is a conditional, they're the same thing. These are equivalent. They're made up of a hypothesis and then a conclusion. So the hypothesis is, it is Friday. The part that goes with the if. And the conclusion is after the then, which is missing. If it is Friday, you can mentally write one in or physically write one in. Matt and Michael are going to the movies. That's the conclusion. No point in writing it again. It's sitting right there. And that's the hypothesis. So then we get into mean math teacher trick world. I'm serious. That's what I call it. We say, hey, let's write it differently. I will go to the ball game with you on Saturday. And you go, well, I don't see an if. I don't see a then. If I go to the ball game, it is Saturday. Well, oh, wait a minute. I'm not. It's very confusing stuff. So you've got to play with it a little bit. See if you can figure it out. Now, of course, we want to get this into mathematical terms, but for me, I'm going to say if it is Saturday, and I am going to rewrite it, and I'm going to put if then in it. Then I will go to the ball game. We get really lazy, or I do. Your hypothesis. I shouldn't say lazy. We get efficient. And this is your conclusion. Should just made a C there. Another one for number x such that 6x minus 8 equals 16, x equals 4. If 6x minus 8 equals 16, then x equals 4. And you might say, I'm starting to see the math now. So that's how we do it. Now, what's deductive reasoning? You use facts and definitions and properties to reach a valid conclusion. We're going to get into this when we start solving equations. And we get a little bit tautology here, which means we say if it's going to be this, then it's going to be that, and then we go backwards and say, see, we proved it. But it's been working for thousands and thousands of years. No, not even. Probably math really been working for the last 300, 400, 500 years. Ancient Greek times is a little bit different. They did more logic, but for some of the equation solving, it's a little bit more recent. We're going to use facts and properties and definitions to reach valid conclusions. And all we're saying is we want this stuff to work. A lot of people are like, just get me through this math and move on with my life. I say, no, we need to make sure we know what we're talking about here. So, use deductive reasoning to determine a valid conclusion. A following statement. If two numbers are odd, then their sum is even. If a valid conclusion does not follow, then say why. So if two numbers are odd, their sum is even. So we can say that 7 plus 13 equals 20, and that is even. Sum of two numbers is 14. Well, we can say those numbers could be, that's my numbers, could be 1 and 14, 13, 2 and 12, dot, dot, dot. So this one's a little more of an open-ended. The other one really made a little more sense. Oh, excuse me, I did this completely wrong. My bad. Got to read the original thing. If two numbers are odd, then their sum is even. So we can just say this is a sum of two odd numbers. Notice we're assuming the original statement is true, which is dangerous to do. And I'll put in a little caveat, could be. It could also be the sum of two positive numbers, two even numbers. Anyway, bigger point is look for counterexamples. Counterexample is a proof destroyed. I'm a little trouble with the handwriting today. By another example. Examples to follow. It's the best way to prove things, because it's really hard to prove something. It's really not that hard to prove it doesn't exist. Using the internet, you own a computer, and all you gotta do is come up with a counterexample. It could be on your phone. It could be at the library. It could be using a friend's computer. We can go on and on and on. If x divided by y equals 1, then x and y are whole numbers. Whole numbers, if you recall, are 0, 1, 2, 3, and all that sort of stuff. Well, they could be rational numbers. We could have 1/2 over 1/2 equals 1. They are not whole numbers. So then we move to our next section. We start getting into other ways to represent mathematics, graphs and functions. With function, I'm going to go my way. I'm sure this is counter to what a lot of people say. I just say it's a good model. And by which I mean we put in numbers and get out good data. We call that inputs and outputs. So for example, I create a machine that tells you, give me the date and I'll tell you what the average temperature is. So we get out one answer. The average temperature today should be 62 degrees. Something that's not a function would say the temperature today should be 62 degrees or 10 degrees. Not a function. We don't get good data out. How do we represent graphs? We could use equations. I mean, we've got all sorts of options. You could call it y equals. You could call it f of x equals. It's an f. More when we get there. So hopefully you know how to do this. This is your x-axis. This is your y-axis. This is the origin. I'm going to do that one later. This is quadrant 1, quadrant 2, quadrant 3, quadrant 4. This is 1, 2, 3, 1, 2, 3, 4, 5, and I'm going to label. This is negative 2, 1, 2, 3, 4. This is 7, negative 1, 1, 2, 3, 4, 5, 6, 7. Notice the x always comes first. This is 3, 0. We call these quadrantals. They're on the actual axes. It's -5, -2. This is 0, 3, 0 left and right, and then 3 up. And this is the origin. 0, 0. A lot of people get hung up on this whole independent versus dependent variables. Don't. Independent is the x-axis. It's the one we put in. Pardon me, the x value. And the dependent variable is the y value. It's the one that we get out. It depends on what we put in for x. That's just how we do it. Well, why shouldn't we do this, that? Yeah, that's just how we do it. So this is the relationship between blood flow to the brain and the number of days after concussion. So we put in number of days. That's our independent. And it shows you that once you've gotten away from concussion a little bit, the blood flow starts to come back to the brain more and more. Dependent variable is the percentage of blood flow. And the order of care at point E is 1, 2, 3, 4, 5, 6, 7, 6, comma, we'll say 100%. 100% is going to go up top. We're not 100% sure on this. Ha ha ha. Wish I'd done that on purpose. That's going to be 6, comma, we'll go with 90%. And that means in 6 days, the blood flow will be back up to 90% of what it was. This is why you got to be real careful with concussions. So just this is how we can represent data. What's the domain and range of a function? Domain is the x values. All possible x values. What can I put in? In the previous problem, I can't put in -2 days. You haven't had concussion yet. It doesn't mean anything. So my domain would have been 0 to infinity. Range, all y values we get out. I actually have this memorized by x domain, y is range. They're alphabetical, x, y, dr. So, identify the independent and dependent variables for each function. Well, in general, the average price of glass slowly and steadily increases through the year. So we say, actually, I can go both ways in this one. I got to think about it for a minute. Well, no, I know what it is. This has got to be time. This has got to be x. That's your independent. And y. That's got to be your price of gas. You look at the year, you say, hey, what is it on July 15th, December 2nd, that sort of thing. Profit of business mix generally increases as the price of a product increases. Not even remotely true, but that's okay. We take our examples. So what's the price? That's what our independent, hey, let's set our price wherever we want. And we say, let's go see what our profit is. Profit depends on the price. Adam earns $8 per hour working up to 4 hours each day after school. His weekly earnings are a function of the numbers of hours he works. Domain, he could have as many as 0 hours. 4 hours after school, 20 hours. In range, he could make as much as $0. 4 times 20, times 5 is 20, times 8 up to $160. So make a table showing the money you earned for the first 5 hours worked while he makes. I guess I'll go with the build table. Hours, $0. 1 hour, $20. 2 hours, $40. That seems awfully high. $8, $16, $3.24, and let's keep going over here. 4, 32, and 5.40. So we can graph this. 0, 0. 1 is, I'm going to have to make these tick marks every 8. You know what? I want enough room to write, so I'll go every 2. 8, 16, 24, 32. Hey, 40. 1 hour, 2 hours, 3 hours, 4 hours, 5 hours. And if I had enough room, I would say stop that about $160, which would be about 20 hours. So there it is. There's a graph. So now we get to analyze graph. The following graph represents the speed of a school bus traveling on its morning route. What's happening? This is speeding up. This is constant speed, so it's at a stop, it speeds up. Then it goes at a constant speed, and then it slows down. And then here it's waiting for kids. Or loading, I should say. Loading students. And this one's the same thing, except no constant speed. It started to speed up, and then it realized it's getting right to the next stop. That's how you analyze a graph. It takes some time. It takes a lot of time to get good at analyzing graphs, so be prepared. Last one, analyzing data by using tables and graphs. When should we use bar graphs versus circle graphs versus line graphs? It all depends. And you'll forgive me when I go non-math teacher. It depends on the data, and it really depends on your boss. I use the word boss a lot. People are like, who are you talking about? When you get a job someday and your boss says, get this data and put it together, you really need to say, well, how do you want me to do it? Here's a couple different ways. And they'll say, no, I really like the bar graph. No, I really like the circle graph. No, I really like so on and so on. So here's a table. It's a bar graph. Number of men and women participating in the championship sports programs. Men is a little bit more, 200,000 plus minus, right about there, and women is right around 125,000, and it's steadily increasing. So describe the general trend shown in the graph. I would say men staying roughly at 200,000, and I would say women starting at about 125. And moving up. You'll look at the data and say, I could have pulled that without having to do a bar graph. And you say, well, sometimes it just becomes more easier to see when we put it into a bar graph. Approximately many more men than women during the 1997-98 year. So that's this one here. And I'd actually go back to the data, about 67,000. What was the total participation in 1989, 1999? This last one, about 353,000, a bit more than that. Okay, so how about a circle graph? Drivers, several cities. Traffic has gotten better or worse, not changed. Almost everybody says worse. Some say not sure. Some say the same. Some say better. Could have done this with a bar graph or not or something. I mean, it all depends on the data. 4,500 people were surveyed. How many felt that traffic had improved? Better be yelled at 8%, so 8 out of 100 equals X out of 4,500. Cross multiply, you should find that X equals 360 people. If a city with a population of 647,000 was representative of those surveys, how many people could be expected to think traffic conditions are worse? Same deal. 63 out of 100 equals X out of 647,000. Cross multiply, get X alone. About 407,610. So we read that. And here's a line graph. It's just an enrollment for some random thing. Estimate the change in enrollment from 1995 to 99. About 14.25 to about 14.9. So we want to say the change. I'm going to go with 14.3 to keep the math simple. About 0.6 million, about 600,000. So it's people who signed up for something. If the rate of growth between 1998 and 99 continues, how many in the year 2005? 98 to 99. Well, that's a bad question because we can already see 99 to 2000. That didn't happen, but fine. I'm going to do this with the table. We were up 0.2. 0.2 to the point where we had we went up more than that. 0.3, we have 14.9. 14.9 in 1999. We should have 15.2 in 2000. 15.5 in 2001. 15.8 in 2002. 16.1 in 2003. 16.4 and then 16.7, and I'm only shortcutting because I'm running out of time in 2005. 16.7 million. So here's how we play with table charts and data. It's not that big a deal. Give it your best shot. Good luck and happy mathing.